It is my pleasure to introduce our next speaker, Nicola Melisivic from the University of Texas at El Paso. The title of his talk is A Continuum of Kunneth Theorems for Persistent Homology.
Thank you for the introduction, and thank you for inviting me to give this talk. Okay, there we go. So just a brief background on my research. I work in topological data analysis, and here's maybe a very basic sketch of a pipeline that we have in topological data analysis. Typically, you start with some data. In my case, it usually was some data coming from biological sciences. So, for example, in this picture, it's a high-resolution fluorescent microscopy image of a single cell. And you try to convert the data into some format that you can do machine learning on it. And the way we do that in topological data analysis is using this tool called persistent homology. There was a previous talk in the morning that talked a bit about this, but the main idea is you have some increasing sequence of simplicial complexes. You compute their homology, and at the end of that pipeline, you can convert all this data into some vector in a Hilbert space, and you can do some data analysis like hypothesis testing, or you can do clustering, or whatever kind of thing you're interested in. I'm not going to talk about the latter part where you do the data analysis part. The focus of my talk today will just be in this middle part, talking about persistent homology and some homological algebra you can do on top of these objects. So what do I mean by that? Is just like we saw before, you have this increasing sequence of simplicial complexes as you vary some parameter. For example, you can vary the distance between between points in a finite point cloud, and you can start connecting points once they pass a certain threshold, and you can measure how the homology of this simplicial complex changes. And we can record this information with a finite combinatorial object, something called a persistence diagram, which measures the birth and death times of different homological features. But more generally than that, we have an object called a persistence module. And really, the main example you should have in mind of that is just you have some space, X, and you have a filtration function F into the reals. For today's talk, I'm going to restrict myself to non-negative reals. And what you're interested in is in the sublevel sets of this function, so these sublevel sets. And you compute the homology of the sublevel sets, and you're going to take coefficients in a field. But more generally than this, everything I talk about today will work for an arbitrary post set. So just some post set P. It doesn't have to be, the non-negative reals. It can be whatever post set you want. And whenever you have that A is less than B, you have an inclusion between these sublevel sets. And this inclusion map will induce a linear map between the corresponding homology vector spaces. And we actually do care about these maps. These maps are actually important for us. We don't care just about the vector spaces themselves. We care about we care about these structure morphisms that we have between the vector spaces. A very important example is something called an interval module. It's a very simple idea. You have some interval A, and the persistence module corresponding to this interval is just a constant, a copy of the field K for all of A, and all the relevant non-zero morphisms are just the identities. Okay. And the reason why we care about these interval modules is because of the structure theorem that we have. So it turns out that if all these vector spaces are finite, which, in case of applications they usually are, then this corresponding persistence module can be nicely decomposed as a direct sum of these indecomposable interval modules. And that's kind of what you saw on the previous slide. These bars here are these interval modules. So that's where they arise from. Now, this category of persistence modules, it's a very nice abelian category. It has kernels, co-kernels. You have a sequence of vector spaces. You just take kernels pointwise, co-kernels pointwise. That gives you a kernel and a co-kernel. You also can compute limits and co-limits. It has enough projective objects, enough injective objects. So it's a very nice category to do homological algebra in. And these objects have been studied from many different perspectives. So people have considered them as query representations. Some people have worked on developing the homological algebra of factors of posets. But it turns out that they also have a connection to sheaf theory. So, for example, gamma sheaves from analytic geometry and microlocal analysis, they have a connection to these objects. And the different people have worked on all these different perspectives in the last decade or two. What do I hope to do with this work is try to import more ideas from classical algebraic topology into this persistent homology setting. So persistent homology as a concept was really introduced some 20 years ago. And it's been, and when people talk about topological data analysis, they mostly just mean persistent homology. But there's been a recent effort in the last decade or so to try to introduce more ideas from algebraic topology for the purpose of applying them to data analysis. So, for example, you have the Euler characteristic transform. People have defined a persistent cup product when they deal with persistent cohomology. And there's also been an effort to introduce persistent homotopy groups in the pipeline. My focus today will be to try to develop a Kunneth theorem, a very useful tool from algebraic topology in the setting of persistence modules. So just a brief reminder for everyone, if you have a product of two CW complexes, it's really just any topological spaces, but for the talk today, I'm mostly going to focus on CW complexes. The homology of their product, remember from the Kunneth theorem, there is this short exact sequence where the homology groups fit in, and this sequence splits. So you can compute the homology groups of the product by knowing the homology groups of the underlying spaces and combining them with this short exact sequence. Obviously, this is just the tensor product of abelian groups and its derived functor Tor. How do I try to generalize this to persistent homology? Is I assume I have a filtration of a CW complex. By that, I mean I have a function from the complex into the non-negative reals. It's constant on the cells, and the map respects boundaries. So the higher dimensional cells must appear later in the filtration than their boundaries. And just like before, this gives rise to a persistence module by looking at the sublevel sets, taking their homology groups, and I obviously have induced maps of homology that are given by the inclusion of sublevel sets. So the central question is, if I have a product of CW complexes, and I have two filtrations on the individual CW complexes X and Y, so I have these F and G, these are the two filtration functions. Is there another filtration function, capital F, on the product such that there is a short exact sequence, not of abelian groups right now, but of persistence modules? So remember, these are sequences of vector spaces and linear maps between these vector spaces. So this is the central question I'll try to answer. There's a couple of immediate issues with this question. Is these are not abelian groups, so what do you even mean by a tensor product of these objects? If there is such a tensor product, can you even define a derived functor for it? Another obvious issue is, if I change the filtration function f, obviously that should somehow influence the choice. It should change the definition of the tensor product itself and its derived functor. And we noticed this in a previous work where we showed that there are two such short exact sequences for two different choices of capital F. One choice was just to add the functions. The other choice was just to take the max of the two functions. Today, I claim that you can actually do this in the greatest generality of all. So you can do this for any order-preserving map phi from R squared to R, and you define the capital F to be this composition. So, in this case, the map phi was just addition or taking the max, but I claim it can be any order-preserving map, and I claim any such choice will produce a different short exact sequence of persistence modules that has the form of the classical Kunneth theorem. To talk about this, I need to talk a bit about chain complexes of persistence modules because I'm dealing with derived functors, so I need to understand how to compute homologies of chain complexes of persistence modules. So when I have a CW complex and a filtration on it, I can construct a very simple chain complex of persistence modules that depends on this filtration. Basically, for any, the chains in dimension M will just be enumerated by the M cells of X. And I have this chain complex of three persistence modules where for each cell, I just assign its filtration value. And I consider the interval module like this. So the interval module that starts at the filtration value of the cell, and it just lives forever. And this thing, because I have the boundary structure on this CW complex, this will give me a boundary map on this chain complex of persistence modules. And in particular, you can, just from the definitions and by construction, the homology of this chain complex of persistence modules will be the persistent homology of the filtration. So just let's be more concrete with an example. Suppose I have this filtration of a triangle. So for example, the vertex X appears at time A0, the vertex Y appears at time A1, the vertex Z appears at time A2, and then the edge between X and Y appears at B0, and so on. You can see from the picture what the filtration times of every simplex here will be. The corresponding chain complex of persistence modules will be the following. So whenever a particular vertex appears, I assign it a generator in the zero chains, basically at the filtration time to infinity. So I have three vertices, so I'll have three of these infinite interval modules, and those are going to be my zero chains. Similarly, for the edges, I have all their filtration times, and I just take these interval modules. And finally, there's only one two cell here, so that's just going to be a single interval module for the two chains. And there's obvious boundary maps here. So for example, how do you map this interval module into this direct sum? Well, you just consider the edge corresponding to B0, which is this edge. It's the edge between X and Y. And the boundary map going from C1 to C0 will just be some alternating sum of the generators at A0 and A1. So it's just very much inspired by the boundary map of that you have in the simple shell complex here. And if you compute the homology of this chain complex, you just get the persistent homology of the filtration. just as a quick exercise, in our case, that's going to be, you have a connected component that lives forever, that starts when the very first vertex appears. Then you have another connected component at A1, but when the edge at B0 appears, they get connected. So you kill one connected component. So that's why this connected component lives only from A1 to B0, and similarly for this connected component. Finally, there is a single, there's a one-dimensional homology class as well. Here, when the triangle appears, that's at time B2, and it lives until the triangle is filled in at time C. Okay. So that's how I want to think about my CW complex filtrations, giving rise to a chain complex of persistence modules. I have to talk a bit about functors on posets. And in particular, if I have one of these persistence modules, let's say G, which is a functor from some poset Q to, let's say, the category of vector spaces like I had before. If I have a morphism between posets, I can take its inverse image. And similarly, if I have a morphism between posets and another functor F on the first poset, there's actually two ways I can take a direct image. And these actually correspond to different ways you can do a Kahn extension over F of this functor. So one is going to be a limit construction. One is going to be this co-limit construction. And these things will actually allow me, these observations will allow me to construct a tensor product between persistence modules that's inspired by some poset map phi. So I have a map phi between a product of a poset with itself back onto the poset. I also have the canonical projection maps into the first and second coordinates. And the very first thing when you want to define a tensor product between persistence modules that you can do is maybe you can just define it pointwise. But that only gives me one definition of a tensor product, and I like to have my tensor product be inspired by the map phi. So what I'm going to do is I'm going to take their inverse images of the persistence modules under the morphisms pi, take their tensor product pointwise in the over the product poset, and these direct images then, in particular this second one, this co-limit construction, will allow me to push this tensor product over the product back onto the poset pi. Sorry, P. And this is my definition of a tensor product inspired by the map phi. And just like I said, it involves this co-limit construction. So there's this co-limit formula. And in particular, if I make for the example when this poset is just the non-negative reals, I can take this component-wise P norm as my map phi, and I can actually, using this co-limit construction, I can actually compute formulas for tensor products between interval modules. So let's just quickly see why this formula is true. So I have this generator at A and this generator at C here, and in these inverse images, they look like a rectangle, this tensor product over the inverse images. And I have to compute these co-limits by looking at the fibers of the map phi over this rectangle. And you can see that once I pass the minimum between the P norm of B, C, and AD, so here, let's say I'm looking at the 2 norm, these are the fibers. Once I'm above that, if I have a non-zero vector space here, there is an image of a generator from a previous vector space here, but this thing also gets sent to 0 with the 0 map. So if this thing was non-zero, it had to be identified with 0 in the co-limit. So that's why nothing survives past this minimum value. And the same thing is true if you change the norm. If you do the p is equal to 1/2 or p is equal to 1 or p is equal to infinity, you get same answers. And these other cases are very, very much similar. You just look at the co-limit definition. Okay, now that I have this tensor product, I can show it's a right exact functor. So it's going to have a left-derived functor, which I'm going to call Tor. And I can compute the Tor between interval modules in a similar fashion. In particular, if I have an interval module from A to B, I can consider its projective resolution, which has length 1, like here. I apply the formula when I tensor with the interval from C to D, like on the previous slide, like that I had here. I just tensor with CD, but now I have a infinity, for example. So I have to use this formula. And that gives me this very simple chain complex of persistence modules. And the homology here, or the kernel of this map, will be the Tor functor between the interval modules. And you can compute it between different cases, and you get this formula. Okay, so now the statement is, if I have two chain complexes of persistence modules, for example, that come from these filtrations of CW complexes, there's a spectral sequence argument that shows that if you assume that one of the complexes is projective and all its boundaries are projective, you can show that there is a short exact sequence. It basically just comes from the collapse at the 2 page of the spectral sequence for the Tor-derived functor. If you also assume that the second complex is projective and all its boundaries are projective, then you can show that this short exact sequence splits. And for the example that I gave of chain complexes coming from filtrations of CW complexes, all of these are projective. Okay, so I can apply this splitting to my example of filtrations on CW complexes. So for example, let's say I have these two very simple filtrations of one simplex. The vertex is born at A1, the second is born at B1, the edge is born at C1, and similarly I have another one. If I take their product, then I get this cubical complex, and I say that if I put these filtration values on the cubes here, the persistent homology of this filtration can be obtained from the persistent homology of the two individual filtrations here by using this formula, and you can use the formulas that I gave you for the interval modules to compute everything. In particular, this has a lot of implications for computability because persistent homology is quite expensive. So if you have a product space and you sample from a product space, it might be more computationally efficient to compute the persistent homology of the underlying spaces and then apply the formula, then compute it using brute force algorithms. Since I focused so much on the component-wise p-norm, this allows you to approximate the persistent homology in the product space with the LP metric. So that's one possible application of this work. I want to briefly just mention something else that I didn't really have much time to talk about, but just like there is a tensor product inspired by the mat phi, there's an adjoint functor that I call eternal hom, also inspired by the mat phi, and it has this. The tensor product had this co-limit characterization. This internal hom will have a limit characterization, and using this limit characterization, you can also compute formulas for the internal hom between two persistence modules, and this gives you and you can show that these two functors are adjoint. So the tensor product with respect to phi is left adjoint to the internal hom with respect to phi, and this dual internal hom has also a corresponding Kunneth formula. There's a short exact sequence that splits if you assume that the first complex consists of projectives and the second complex consists of injectives. I wanted to briefly give an application of this as well for this dual internal hom functor. It turns out that it can compute the persistent Borel-Moore homology of certain filtrations of non-compact spaces. So for example, let's say that X is a simple shell complex and T is a subcomplex. If H is the difference, so just X minus T, then the Borel-Moore homology of H is defined just as the relative homology between X and T. So there's other different characterizations of Borel-Moore homology, but because I'm dealing mostly with simple Schur complexes, I'm just going to stick with this one for today. And it turns out that if you take this persistence module and you take the internal hom of the chain complex of the filtration F that's coming from some filtration, that's a filtration on a CW complex X. This is kind of like taking coefficients, but you're taking coefficients in a persistence module, not like a different group or something.
You have 2 minutes.
Okay. It turns out that the Kunneth theorem that I gave you on the previous page can compute the persistent Borel-Moore homology of this induced filtration. So I had this original filtration here. This cochain complex now has this corresponding reverse filtration. And I claim that the persistent Borel-Moore homology of this filtration can be computed using the Kunneth theorem I gave on the previous slide. So for example, here at this filtration value, you see that there is a homology in degree 2. That's because the Borel-Moore homology of this, it's actually the same as the 1-point compactification, which is a sphere, which has homology in degree 2. And I just want to advertise that this is a very recent preprint. It's only been up for maybe about 2 weeks. And I think I'm done. Thank you. Thank you for listening.
Thank you for the nice presentation. Let me stop the recording.